Now we introduce self-supervised visual planning. If a robot can predict future observation and select action, it means it can fully understand the environment and predicts the effect of environment on the robot action. We now use a visual model predictive control, MPC in short, to predict the observation and select action. For example, we have an object in this image. We specify his initial position and specify his target position. We want to know in each step when we select an action, we give active neural action, select action, and how the observation changes under that selected action. Let's say we have in a frame this frame at a time t, we have a pixel, and when we select action at this time step, we want to see in time step t+1 where this pixel should be. So we get, for example, we get a probability distribution. To get this probability distribution, that means we predict the motion of the selected pixel or object. We have to first predict mask. The mask means what's the value distribution or weight distribution, and we also need to do a transform. Transform means we need to calculate at t time step. Here is the initial position and what's the target position after we select the action. So it's two steps, and then we, for example, we show the procedure in this figure. For example, t step, we have this image, we have this object. To predict the target position in the next step, we first we do a transform. That means from t to t+1, what is the position, and then we predict the mask. Mask means if we keep the same position, what's the appearance, and then we combine this position and this mask together. We get at a time step t, this object and his position, and we get the position and appearance at the t+1 time steps. So right now, the basic idea is for each pixel we do the same similar transformation, use a neural network. Also, we can do it by object by object. Each time we predict the one pixel or one object. So the architecture of the visual model predictive control can be in this way. For example, we have a input image, and we use a convolution network, or we combine with the convolutional LSTM together to predict the image or object movement in the next step. And here we first we extract the features from the input image. And because we right now we want to know or predict in the false state and this action. That means we give this action. What's the next observation? That means the object we are interested in, how can move from a time step t to time plus step t plus 1 by selecting this action under condition, the four states. Part of them is observation, part of them is the inner state, like the joint angle or position or pose of the arm. And then follow, this is the downsampling, extract the feature of the input image combined with the inner state together, and then we predict the mask. Now you say this mask is for each one is corresponding to the one pixel or one object in the input image. And this is just for the mask. The mask means the weight distribution. To predict the motion of the object, we have to do the transformation. From here, we calculate, we get the kernel. We operate the kernel on the input image, we get this transformation. This transformation work with this mask and input. That's this initial value, the initial image. This is like a background. Together, we predict the observation at t plus 1 time steps. And in this way, we can, based on the observation and the inner state together, and for the action we selected at a time step t, we can predict, the object from, this in this input image, and what's the position in the image at a time plus 1 step. That's a basic idea. For example, if we work on an object, because object may include multi pixels. All the pixels in one object, they follow the same transformation. That means they follow the same way to move from one step to the next step. We need to calculate the mask. And mask means we calculate the value at each pixel and combine the mask with the transformation. We got what's the position in the next step. Also, we can use the spatial transformer we introduced previously. Can use it to predict the transformer parameters. Parameters, then we get the transformation matrix. The matrix can calculate between the source pixel coordinates, and this is the target. This is the coordinates of the target pixels. We can they have the relationship denoted by this transformation matrix, and then we can know from t step in the image we calculate what's the object position. Then we can predict what's the position of the same object in the next image. For the more detailed information, can check with this reference. Thank you. Bye.